So in this video, I'm going to introduce you to the idea of regression lines. So we are going to use technology in order to find equations of regression for sets of data. So what I have here is actually the same graph repeated twice. And in blue, I've got a scatter plot. So we've got a series of points, some data, x and y values that go together. And in this case, they do seem to have a bit of a tendency. It's not perfectly linear, but we can come up with an equation, what we're going to call a regression line, that can help us use this data to make some predictions. And how accurate those predictions are is going to vary depending on the data. And we'll talk about that a little bit too. But I can actually do this regression two ways, and they have different uses. So the regression of y on x is the most common one we're going to do, and that is where we are using x as our independent variable, which is the standard, and then independent, and then the y would therefore be the dependent variable. And what that does is that will allow me to come up with an equation that's slightly better for using x values to predict y values. If I go the other way around, then actually what I'm doing is I'm treating y as the independent, which is somewhat unusual, but would be useful if I were wanting to use y values to predict x values. So x would be the dependent variable in this case. In each case, I'm going to end up with a slightly different equation. So this graph is actually the same graph. It shows the exact same line. The two regressions would give me slightly different lines because they are trying to do different things. If I'm doing a regression of y on x, what it's essentially trying to do is reduce the vertical error. So each of these points, data points, has a certain error with this equation. Some of them are very small, like these 2 points right here, this point. These ones have very small error. These other ones have bigger error. But what a regression of y on x is attempting to do, it uses technology to sort of minimize the average vertical error. So it means that this is better for predicting y values because it has minimized the error in y. If I go the other way around, because there's also x error that I can consider, again, the points that are very close have minimal error, but this one I can think of as, okay, well, there's horizontal error for a bunch of these points. Some of them, the horizontal error is actually way off this line. So for example, this one would be the horizontal error. And a regression of x on y is attempting to minimize the horizontal error, which makes this slightly better for predicting values of x. So they are going to get slightly different equations. What is going to be true of all of these equations, or both of these equations, is that both will pass through, so both equations will contain the point, the average value of x, and the average value of y. So this notation where I put a bar over basically is used to mean the mean. So the mean value of x and the mean value of y will be contained on both of these equations. So that is essentially where they will intersect. If I find the average of all the x values and the average of all the y values, that point will be on both lines. So let's look at an example of some specific data here. So this is data taken from one of my classes, a few of my students, their arm span in centimeters and their height in centimeters. And it's not very many data points, so it's not super useful for predictiveness, but it can still help us to illustrate the concept using technology. And that will be different depending on what kind of technology you're using. So if you have a Casio calculator, or if you have a TI calculator, or if you're using Microsoft Excel, or if you're using Google Sheets, there's going to be slightly different ways that you have to go about finding these regressions. And that will be treated separately in separate videos you can find online. So we have the equation of the regression of y on x. So in other words, if I'm treating the arm span as the independent variable, because realistically, I mean, I've organized these so I put arm span before height. But there are times when I would want to be using arm span to predict height, and there are times I would want to be using height to predict arm span. So depending on which one I'm wanting to use to predict the other, I'll do the regression in a different order. So the first one would be if I was wanting to use arm span to predict the height, so I want arm span to be the input in the equation. This is sort of our usual linear equation that we're used to seeing. So this slope would represent delta y over delta x. So in other words, what is the change in height for every, like centimeter change in height for every centimeter change in arm span? And we've got a slope of about 0.404. So what that's saying is for every centimeter change in arm span, you would expect to see a 0.404 centimeter change in height. And then this is where it gets a little weird in terms of predictability. The y-intercept would be what is the height when the arm span is 0. Now, obviously, you do not have, on average, humans do not have a height of 1 meter, 103 centimeters, when they have no arm span. So the predictability of this equation gets a little fuzzy out towards the edges. This R value right here of 0.336, so R is it's a correlation coefficient, essentially correlation being how closely do these data actually relate to each other. And this is quite weak. So this is a very weak correlation. So that means the predictive ability of this equation is pretty low. The fact that it's positive, though, is important. The positive correlation is tied to the positive slope. It basically means as arm span goes up, height goes up. As if I had a negative value, that would mean that as arm span goes up, height goes down, or vice versa. The best possible R value you can get is either 1 or -1. 1 or a -1 would indicate that we have data that perfectly fits the equation of the line. You can kind of think of it as a 100% correlation. Good correlations would have values like in the 0.8, 0.9 range, but 0.336 is very weak. And I get the same correlation on both sides, whether I do regression of x on y or y on x. So when we see an R value that low, we have to take care with how we are using this to make predictions. But with that first equation, if I wanted to say, okay, well, what would I estimate the height to be for somebody with an arm span, say, of 160 centimeters? Nobody in my data set had exactly 160 centimeters as their arm span. So what I could do is I could predict that the height would be approximately 0.404 times 160. And then I would add the 103, and that would give me approximately 167 centimeters. So I could make that prediction. Again, I would take it with a grain of salt. It's not a strong prediction, but it's reasonable to assume they would be somewhere in that vicinity. If I used the regression that goes the other way around, that would be, let's say I have somebody that I know has a height of 170 centimeters. Y equals 170 centimeters, say. And that, again, is not a specific data point in any of my list here, but I could plug that in and say, okay, well, then I would predict their arm span to be about 0.280 times 170 plus 123. And what I would get in that case, let's see, 0.28 times 170, I would get approximately 171 centimeters as their arm span. This y value would be the height. I do want to talk about if I switch the x and y. So if instead of having this be in the form y equals mx plus b, I have x equals something y plus something. This something would now be the x-intercept instead of the y-intercept. So in other words, it's saying that if the height were 0, the arm span would be expected to be 123 centimeters. Again, obviously nonsensical in this concept, so we have to be really careful when we take our predictions out to the edges. And this slope right here would actually be measuring delta x over delta y. So that would be saying for every centimeter change in height, I would expect to see a 0.280 centimeter change in arm span. And the mean values of these are found in both equations. So I will note these equations are not just rearrangements of each other. If I rearrange this first equation to isolate x, I am not going to get the second equation because they are calculated differently. They're using different measures. They're trying to minimize different error. However, both of them, if I substitute into the first equation, 0.404 times 171.2. Now the 0.404 and the 103 are rounded values from what I got using technology, but I would get approximately 172.5. And certainly if I used the unrounded values from my calculator, that's exactly what I would get. And if I substitute the 172.5 into the other equation, so 172.5 into the regression of x on y, and then add the 123, I would expect to get approximately the 171.2. Again, it won't be exact in these numbers because these are rounded values, but it'll be pretty close. All right, and then the last thing I just want to mention, I've kind of said it a couple times, you have to be really careful how we're predicting, and there's a difference between what's called interpolation and extrapolation. So interpolation is using values within the data set. And what I mean by that is the two examples I gave before were interpolation. So 160 wasn't one of my specific numbers, but it was in the range of the numbers. So I had numbers smaller than 160, I had numbers bigger than 160. And the 170 centimeter height, again, was within. So I had heights that were less than 170 and heights that were lower than 170. Interpolation is a little more valid. It's assuming that for values that are close to the values I already have, this equation is going to be reasonably good at predicting. Extrapolation is using values that are higher or lower. And that's essentially what I was doing when I was talking about the x and y intercepts. So if x equals 0, well, 0 is well outside the range of the values that I actually have for arm span and for height. So if I'm using 0 or even a number that's quite a bit larger, like predict the arm span of somebody with a height of 212 centimeters, that would be an extrapolation. It's going outside. We have to be much more careful with extrapolation because typically our equations of regression will have a limited domain and range within which it is appropriate to use them to predict.